I will briefly talk about multilinear regression. So here's a data set where many different bream fish were measured in their weight, length, height, and width. Okay. And what one wants to do is they want to use the information of length, height, and width to predict the weight of the bream fish. Now, why would anyone want to do that? Well, maybe they want to classify or sort the fish that they caught into different different bins according to their weight, but trying to measure them one by one takes too much time, whereas just taking a quick photo and making the machine measure the size of the length, height, width is much faster. So it would be nice if the weight can be predicted just from the length, height, and width. So such a problem, assuming that you have a linear relationship between those variables, it's called a multilinear regression. And it works like this. You're trying to predict the value of y by using a bunch of x1, x2, x3, a bunch of predictor values. So let's say x1 is the length, x2 is the height, and x3 is the width. So what we want to do is we want to write down the predicted weight of the bream fish as some number plus beta 1 times the length plus beta 2 times the height, and then beta 3 times x3, which is the length. Okay. So let's try this. Now I'll explain the theory behind this a little bit more next time, but the formulas obtained here is obtained in the same way we did for the regular linear regression, which is that the usual linear regression, we use the sum of squares of error, right? Which is you take the y minus y hat squared, right? And you add them up. That value has to be minimized. And if you try to find the minimum using derivatives, because when you find the minimum of a function, the derivative is equal to 0, right? And then in the class, I calculated the derivative, set them equal to 0, and eventually I got the formula for beta 1 and beta 0, right? That was a simple linear regression where you didn't have more than one predictor. You didn't have this much. You only had beta 0 and beta 1. So for those, I have demonstrated the formula. I derived the formula using the calculus. But now, what do you do if you have beta 2 and beta 3? Same exact deal. You again take this y hat, subtract from the actual value y, take the square, so you have the sum of squares of the error, and you take that function, you differentiate with respect to beta 0 and beta 1 and beta 2 and beta 3, set all of them equal to 0, set them as a system of equations, and then eventually you get a solution. And what ends up happening is that because it's the equations that you get is a system of linear equations, the solution comes out as some matrix products, big matrix products. You know that system of equations can be solved by using matrix inverses, right? So the formulas end up being just that, some matrix calculations. So I'll probably not be able to show you the calculation because it's too long, but I will show you the formula for getting these coefficients, what happens if you do that, okay? Now, today what I want to show you is just to see how in Excel you can get such a thing. And the output of the Excel, I have to explain what the output of the Excel means. Okay, so how do you get the multiple linear regression? Well, default Excel can't do it. What you need to do is you have to install something. So you have to find toolbox or something. Add-ins. You have to go to add-ins, and you have to install analysis tool pack. If you do that, once you have the analysis tool pack installed, then you get a new item on the menu. So if you click data, there's a new analysis portion, and there's this data analysis, which you can click. And in the data analysis, there are several things you can do. I think, there are like pair to sample means. Some of the other tests that we've learned in classes are also here. You can use them. But what we want is simply just regression. Okay, so we're going to choose regression. And since we want to predict the weight, input Y range will be this one. Oh, by the way, you probably want to include a header so that the output is easier to read. So you do this, and then we are going to click the label so that it knows that the very first part, it knows that the very first part is a label. And then for the X range, it's not just length, but it's length, height, and width, so you have to select all of them. So this will be your X. And then that's it. You now, you can also do residual plots if you want. Let's try this one. Okay, so if you execute this, it's going to make new graphs, and these are the residual plots. So this will be it's changing the various values of width and finding the difference between the predicted Y value and the Y value. So that's the Y minus Y hat plotted along the width axis. There's the same data set now plotted with different axes. So those residual plot can be shown. And you really just want to have such a plot just to think about normality. So both simple linear regression and multiple linear regression, they rely on the assumption that the error has the distribution of a normal distribution. So you have most of the error close to zero. You have occasional error that are very far from zero, but they occur much less often. So if you redraw the error with respect to the value of the error, if you make a histogram, you'll see a bell curve just from here. So that's a good thing. Okay. All right, but here's the important part. Let's read what these are. Okay, so first of all, multiple R. That's the regression coefficient. Okay, it's the R value that we talked about. Is it very? What does this say? Do we have? Do we see linear regression, or are the variables linearly correlated? They are. It's very close to 1, right? Yeah. So this is actually quite good. Now there's the R squared, which is 0.942. What does that mean? 0.942. R squared tells you what?
How much is not
the percentage of data that
is explained by
is explained. So this is what's called the coefficient of determination, and it means the portion of the variance in y that is explained by the linear regression. That's what it means. Okay, we talked about this last time. I showed you that the variance of y has two parts, right? Variance of y is sum of squares of r and sum of squares of error. And therefore, if you take the ratio of sum of squares of r divided by sum of squares of y, then you get this value that's between 0 and 1, which is like the proportion of the variance of the linear regression in the variance of y. That's what it means. Now, under that, there's something called adjusted r squared. And this is another quantity that becomes usually they're very similar to, these two numbers are very close, okay? R squared is close to 0.94. This is also close to 0.94, right? But what it does is that if you throw in more predictor variables, so let's say you add a new column in the breamfish where they measure the length of one of the fin. So you have another predictor, right? And the more predictors you add, just because you added more information, you end up getting better predictions, okay? Just because you added more. But then that additional predictability might be nothing more than just because you know more data. Yeah, it's something called overfitting of your data. Yeah. So if the R squared is artificially being increased just by adding more predictor variables, we have to penalize it somehow, right? So adjusted R squared does something like it does something with the number of predictor variables. So it become the more predictor variables you have, this value will be slightly lowered. Okay, so when you have multiple linear regression, the adjusted R squared is a better value to use for the coefficient of determination rather than the R squared. Okay, so hopefully in an exam, when there's a multiple linear regression question, and I ask what percentage of the variance of y is explained by the linear regression, or what percentage of variance in y is explained by y hat. If the questions come up like that, then you should be using adjusted R squared. Or if that's not available, you can just go back and use R squared. Hopefully I'll just have one of these available, but if they're both available, you use the adjusted R squared. Okay. Okay, now the standard error. This is like the sum of squares. So this is SSE. Observations, 35. So that's the lines of data that you have. Where is it? See, this thing ends at 36, but the very first row was used for the header. So we really have 35 observations, right? So that's the observations. So that's the lines of data. And now there's the degrees of freedom. There's the regression degrees of freedom, which is same as number of predictor variables. So we had length, width, and height. And then there's the residual degrees of freedom, which, let's say if this is empty, if this is unknown, then you just have to do total minus the regression degrees of freedom to get 31. So these two have to add up to 34 because that's total, of course. But the total degrees of freedom is always n minus 1, okay? So since there are 35 observations, total degrees of freedom is 34. Okay, and the regression degrees of freedom is number of free variables, and residual is total n minus 1 minus the number of predictor variables. So that's the residual. Okay? And then the sum of squares. Sum of squares of regression is simply you take the sum of squares of the length, width, and height. So for each fish that they caught, you square these and add them up. Okay? And then mean squared is whatever you get from here, you divide it by the degrees of freedom. That gives you the mean squared. Okay? Whatever you get from here, you divide by 31. That gives you mean squared. And when you take the mean squared and divide it by the so when you take the regression mean squared divided by the residual mean squared, you get this value called the F test statistic. And I will explain what this F test statistic is next class. And from that, we can compute the significance F, which comes out like this. Okay. And then here the values are negative 1046, 12, 62, 45. These constitute the values that we wanted. So the equation now says that if you want to find the weight just from the width, height, and length, then the formula is that you have to do y hat equals to negative 1046.6 plus 12.03 times x1 plus 62.81 times x2 plus 45.9 times x3. And that's the equation. Okay? This equation will give you the weight, and the company will be happy because the correlation coefficient was 0.97. So it has a very good prediction capability. So the prediction is very good. Okay? And then there are some other values here. Let me just talk about this one. I don't know why it repeats the same thing twice, but these two values are the confidence interval for each value. So I have the coefficient beta 1 as 12, but you know, this is all just the estimate you get from your sample, right? So if you were to increase the samples and you get bigger and bigger sample and get a better feel for what this coefficient should be, where do you think it would belong? With 95% confidence level, you know that the true value of this coefficient lies somewhere between negative 3.5 to 27.5. That confidence interval is rather large. Yeah, but that's what it says. Usually it's not such a good thing to have such a big difference between the two upper and lower bounds of the confidence interval. And the reason for that is partially because the length, height, and width are so correlated, and that's something that's not good for doing the multiple linear regression. I'll explain that again next time as well.